Perfect. Well, welcome and thanks for inviting us back again. We're going to get to who we are later, who don't know us. This title was not generated by ChatGPT, and this may lead you to what we're going to be talking about, because most of the talks that talk about this topic do the trick of doing the first few slides in AI, and then, haha, it's all been AI. We don't do that. This could also be called Connecting Houdini to the Latent Space, a Hitchhiker's Guide Part 3. Part 1 and 2 we presented together with Chris Hoffman at OFF, and this is Part 3 for you. I think you're the right audience for this. Before we start, thanks so much to SideFX for enabling this whole project. And welcome to you guys. So brace for papers, Python, and PIDA testing. We are professionals. The people who don't know me, I run, together with a partner, I run a learning platform called Entagma, like, comment, and subscribe. We do learning content on Houdini, on procedural design, and recently on generative AI topics as well. And I teamed up with this guy here.
Yeah, hi everyone, my name is Ambrosiussen. I'm a technical artist. I really like building tools for Houdini, for real-time engines. I used to study here at NHTV back then, now BUas. Then I went on to working with SideFX for 5 years, where I was the lead for SideFX Labs, built lots of tools, spoke to lots of studios. And nowadays I have my own company where I help others create really cool stuff at big scale. And we built something really cool that we'll show you today.
Yeah, so end of last year we had a great idea, or so we thought, because back then AI was just running hot and we were thinking like, let's do something, but let's try and get away from this cold. So we had this idea, and this is the real recording from back when we pitched it. And the guy on the one side is Paul, the other guy is Chris Hebert, Senior Director of Marketing at SideFX.
Hi, so yeah, thanks for having this call. So I'm guessing you've heard about the Monte Carlo algorithm, haven't you?
Of course.
Right, so we would like you to take us to Monaco with a budget.
And this is the actual call, right? This was not rehearsed or anything.
That clearly is a person who is convinced. So let's call it a few negotiations later. We ended up here. Paul just went down to what he thinks is the place we're staying. There's no one there, and he claims to have found the keys to this apartment.
I just went into this property.
And clearly, this man is trustworthy. So we ended up in the mountains of southern France, which was kind of a brave move to have us two in a mountainous hut. Especially when it comes to setting up shop in a mountain hut. I mean, it wasn't a proper hut, but you run into issues like this. So this is us testing the Wi-Fi, or the not-so-wireless-Fi. And it ends up at 8 megabits down and 0.6 up, which is great when you're trying to work with AI, because you have checkpoints that are 5 gigabytes and you download multiple of them. What do? We panic. We call the landlord and we get a 5G router, and that solves it. But actually, what do we do with a project? And we panic again, because anything that we thought of would be interesting in December when we pitched this is now all out the window, because AI just moves too fast. So we start researching, and some of you lift your hands, who knows that? This is Web UI? Okay, cool, a few of you. So that's a Stable Diffusion interface, which is really popular, it's really easy. I urge you, whoever wants to dip their toes into AI, use this one, really, really nicely usable, really great tool set. But also, recently, we discovered this. So there's another branch just tearing apart this whole diffusion pipeline that creates images into individual nodes. And this whole thing, this as well as this, is based on an underlying library that came out, I think, last year or 2 years ago. It's called diffusers. And this has the great advantage that it unifies lots of tools with generative AI under one common framework. So what we set out to do is, we thought, well, we know nodes, and Paul knows Python. So how about we build this, your bread and butter diffusion node tree, in your most loved software?
Yep. So we did a lot of research on what we saw, in those earlier things with Comfy UI and the web BUI. And what we ended up doing is basically look at the whole pipeline of Stable Diffusion and look at the individual elements and see how those work. And we thought, can we actually represent those as individual nodes in Houdini, similar to the Comfy UI, but have it be represented as geometric data in Houdini that we can do all sorts of operations with. Because then we can't just modify some sliders and do some drawing and have that affect the Stable Diffusion process, but we can use literally any operator in Houdini to do things with it. We can drive terrains, we can do simulations, we can do compositing, we can do rendering, we can do literally everything, and Houdini already has this giant library of tools that you can use things with. So what you see here in this node graph is essentially various nodes that do various different things, which we'll look at individually in the next couple of slides. And we'll also show you, now that we have access to these underlying data structures that Stable Diffusion uses, what happens when we play around with those. So here you see just a very basic example. This is, it's useful, but we can do much more interesting stuff with it. So here is one example of the more interesting stuff you can do with it. So once again, we start with our prompt node where we can type in a prompt, a cyberpunk forest, digital art, hyper-realistic. We then use our node called control net conditioning, which can extract a depth map from that image. We then use that depth map to, for example, offset all those points, that image that we've reconstructed. We then offset some that to make it look really nice, like, for example, a lighter point cloud, and you have something that looks really cool. This, of course, was done by one of the beta testers that we invited really early on to sort of try our new tool set to do some cool stuff with it, and this is what you get out of it. Now, once again, since this is Houdini, any network that you build, you can just reuse, right? So go back all the way to the top, change the prompt to be something else, and you now have a completely different 3D scene just like that. Just have it recompute and you're good to go. Once again, you can either manually type in a new prompt and you get something else, or drive everything using other procedural systems in Houdini.
So when I usually go into projects, I just start doing stuff. And this time, I decided it was wise to team up with someone who actually knew their shit, and Paul insisted that we have a strategy when we start out. So this is what we came up with.
Yes, having a strategy is wise. So the first thing, of course, for me, since Moritz already had done much more research into Stable Diffusion and its underlying technology and how it works and what are all the individual elements, I was sort of like this monkey when I joined him, right? I was sort of there to look more at the integration and the Python code and the tool building and such. But Moritz really already had a good understanding of how everything works. So we had some sessions where he was teaching me the inner workings of Stable Diffusion so that I actually knew, what are we going to be building. So once we understood that, like I said, we really wanted to take apart and rip apart the Stable Diffusion pipeline as a whole and make it modular, right? Just like we saw with the Comfy UI. So what we did is we just opened up a Miro board where we looked at, okay, what are the individual things that people might want to be playing around with? Of course, having a prompt, being able to manipulate that or drive that using attributes, that makes sense. The tokenizer, what does that produce? It produces certain attributes, which we'll see in a second. Maybe you want to be able to manipulate those. So perhaps we want to have a node called token manipulate to do some, cool stuff with that. Same for images. We want images to drive this process. What is the data that comes out of it? We have some things that we said we definitely want to have this, but some other parts, if we have the time, we'll do this because we only had 9 days, of which I think 5 days of actual development. So, we really had to sort of create the MVP, right, for what we wanted to develop.
So for me, this was a very interesting period because, I'm a script kiddie, so I did like my small tools for myself, but I veered once into developing a tool set, which I now don't develop anymore, so make of this what you want. So I asked myself, generally, how does Paul work?
Generally, how I work when I build something like this, I don't care at all about user experience. I basically just build something that feeds into the next thing, that feeds into the next thing, and then once I know the entire thing is working, I then just build my own thing and replace it, because then I can basically crunch out stuff like this in half a day, whereas most people, if they build it from scratch, it'll take a week or something, right? And then it's very easy to see, okay, this is not going to work, let's try that, pivot here. That's why this is so effective.
Also, by the way, glass doors in the kitchen, a really effective whiteboard if you don't have one.
Yeah.
Use Windex though when you leave the place.
Yeah, I think the owner of this place probably was very happy with us because everything was cleaner than when we arrived. But to summarize sort of the strategy in one word is essentially agile development, right? That's what we really wanted to do, and that's what we actually also ended up doing. So now let's take a look at the individual nodes and see what they do. So what we see here on the right side is a node called Stable Diffusion Prompt Create. Now, what does this actually produce as an output? Very simple, 1 point. And that 1 point has an attribute called prompt, which is just a string. Now, nothing fancy about that, but it is, native geometry and native attributes in Houdini, which means now we're basically starting to move that Stable Diffusion pipeline into Houdini. Then once you have your prompt, which is your human language, right, where we describe something, we can say, this has to be red, or it has to be a person, it has to be a giraffe, it has to be something else, it has to be photorealistic. These are words and sentences that we understand as humans. But when we want to use this in an algorithm to create something out of it, we need to translate it into a format that machines understand. And usually these are called input vectors, and these are usually floats because these are very easy to work with, you can blend with them. But in Stable Diffusion you have this intermediate step called input IDs, and the process of converting our human readable language to some other process is called tokenizing. And tokenizing creates these integer attributes. And what do these integer attributes represent? Well, all it really does essentially is it looks at your words, right? It chops it up into pieces, not necessarily per word, but maybe half a word with something else. For example, there is, or cat, or whatever else. And then it looks at a giant data table, right, of words that it understands, that it has been trained on. And then basically there's a lookup table where it says the word cat means 5, or this other word or this combination of words means this number, which now means that we have really cool integers to work with.
Really cool integers to work with means that you can start messing about with the AI and the AI generator. For example, take this where I prompted for a pigeon wearing, or a parrot wearing to see a tuxedo. And as Paul mentioned, you just get this prompt string first, and then you turn it into those tokens. And you see the token structure is you have this fixed start and fixed end token, and then zeros where there's no parts of a sentence. And in between you have these seemingly random numbers between 0 and 49,000 something. And Paul also built a node that converted those numbers back into a sentence. And you see my prompt comes out here. Why would I want a detokenizer? Why would I want to generate a bunch of words out of integers? Because I can generate those integers randomly and feed those in. So I just generate a bunch of tokens that I prompt randomly and see what comes out of this. In this case, for example, Matthew congestion equals any added off-road rig growler burn Mexico stairs, which is this. So once you play with this, this is the first layer of interface with your AI that you can play with. So not only can you do that, this is just randomized tokens at this, and I just didn't write them down at this point because there's something like whatever this. Yeah, this is brilliant. I have no clue. I literally should have written this down. I have no clue what. I mean, yeah, this and this, yes, okay, and you also end up with quite aesthetically pleasing things. So that's the first layer that you can mess around. But there's another one.
Okay, so now that we have our tokens, right, this intermediate step, we now need to encode these into a format that is actually understood by the model. And so for our prompts, you use a node called text encode, and this is going to create what's called text embeddings. And text embeddings you have generally 2 of, one of which is optional, but we have conditional embeddings as well as unconditional embeddings. And as the name suggests, you can already sort of guess where this is going. The conditional embeddings are basically things that you do want to see, whereas the unconditional embeddings are things that you don't want to see. So we can now also see that the text encoder has 2 inputs. We have a prompt create on the left with a tokenizer, as well as a prompt create on the right with a tokenizer, both of which are basically the same nodes, but in one I specify things that I do want to see, for example, a forest, and on the right I can specify I don't want to see any dogs in the forest. I like dogs, by the way, but just an example.
And the text embeddings that this thing spits out, it's like a few thousand or a few hundred attributes, float attributes. They are amazing. Because what you can look at them is, you can look at them like coordinates in a semantic space that describes the world model that your AI has been trained on. So think of the latents as a point in 2D space in this example. And we take these 2 parameters, in reality it's a few hundred, a few thousand parameters, and we throw it into our AI algorithm and generate this image, for example, this parrot here. So the idea is, what if I randomly scatter a bunch of points close to this coordinate that generates the parrot, and then turn those into an image? Can I get some information, or can I generate some images that resemble this? Can I get some information out of what does the AI or the AI training segment around or cluster around this parrot? And it starts off absolutely normal, well, a bit creepyish at times, sometimes even more aesthetically pleasing images. But then the further you go away randomly, it veers off. I mean, arguably this is aesthetically pleasing, but yeah, you don't know what exactly it is, and once you get far away from the parrot, you end up like this. So really abstract forms. I don't want to call them noise yet, but you get away from a readable image. Also, embeddings allow you to do a fun thing called prompt arithmetic. So what you can do is you can add, average, multiply, work with those embeddings. They are just float values. And in Houdini, they are just point float attributes that we exposed. So what you can do is you can drop down 3 tokenizers and do this, king minus man plus woman. Let's go through this. This is a prompt for king. This is a prompt for man. And this is a prompt for woman. If we do the arithmetic, king minus man plus woman, we get out this, a queenish looking picture. So not only are we able to do semantic algebra and algorithm and arithmetic now, we are also able to mess with this. Because what if we weigh down the king minus man thing and add 2 times a woman? I was expecting drag queens too. But what this does is it's something wonderful. It's something we just discovered recently. It generates this. Or this. And to me, this is amazing, because I see a space that's worth discovering and that's worth exploring and mapping out and seeing what's going on there, because this is stuff I wouldn't expect with that prompt. And it has an eerie beauty to me. And these are actually fully converged images, so this is what the solver spits out. I mean, of course, debatable if and how you want them to use them in production, but from an artistic, from a design standpoint, this is, to me at least, extremely intriguing. Let's go on to our next node.
Yes. So now that we've played around with those, when you're doing a solve for Stable Diffusion, you need to start with some starting noise, right? Because the process of Stable Diffusion is essentially getting from a very noisy image, right? Or just plain noise like this, and diffuse it into something that actually makes sense for us. And so to initialize a simulation solve like that, of course, you can use the starting noise that is typically used by Stable Diffusion, which has a very specific distribution of noise itself, and guide that to feed the image. But what happens when you actually swap this noise that we know works with our custom stuff?
So the custom stuff is just your standard Houdini X noise, written out again as point attributes and fed into the whole algorithm, again with the parrot prompt. So this is what happens when you take that X noise and just scale it. So you end up with stuff like this, pictures that definitely are readable, maybe not as clear as the stuff that was initialized with the statistically correct noise, so to speak, that the network was trained on. But again, the further you veer away from that input noise, the more you get into this uncanny territory to see what your algorithm actually produces out of these input latents, out of these input features, until you arrive at something like this, which is, well, graphically quite interesting, I'd say. It has nothing to do, or it's maybe an interpretation of a parrot, but clearly not the one-on-one visual representation anymore.
So far we've seen, one way of, or essentially 2 ways of driving the generation of an image like this, right? The output. We've seen that we can provide a prompt, right? Something that we understand and we can describe. I want to see a person in the forest with a hat on, broken his leg, whatever it is, we can use that. We can change the noise, right? To a different seed perhaps, which will give us a different looking image, but that may not be exactly what we want to do. We want to guide this more with, for example, some additional attributes or data, right? So we have this other node called image to points, and all it really does, very basic, it just takes your image and it creates a grid of points, once again, native data type in Houdini, and allows you to use that. Now you can use this to, for example, import your own image, a portrait in this case, or to, for example, import a mask, which you can see later on, you can actually also use to guide the solve to only solve Stable Diffusion in a particular area. For example, if you want to just add a beard to someone's face, or you want to add a hat to someone's face, or you want to swap out someone's t-shirt or whatever it is. Now, once you have those images, once again, in a format that we as humans understand because we see things in that particular encoding or format, we need to encode this, once again, into latent space that the solver is trained on, right? Once again, float values from negative to positive that we can do something with. And so the image encoder gives you basically 4 channels that have been essentially noised in a particular way so that you can use these as input for your solver. That is one type of input you can use. So these are called guide images in our system. Additionally, Stable Diffusion has this additional addition called ControlNet. And ControlNet allows you to really control, like the word says, the solve of Stable Diffusion even more. So you can do various things. You can, for example, feed into it an image of a skeleton of a person. And what you will get then as the output of the solve is a person that has that exact pose. So what you can do is you can, for example, in Houdini with KinEffects, pose a character, the way that you like it, and then you can use that to drive the generation of an image that actually matches that. Similarly, you can also, for example, using Attribute Create or Attribute Paint, paint your own little sketch of something you would like to see, or perhaps some particular shapes or an object you would like to see, which together with the prompt allows you to really get a result you like. And then once again, here's some other examples. We have a canny edges that you can also feed into it to sort of really get particular shapes or silhouettes or contours to be present. Similar for the image on the right, as well as a segmentation mask. Now, the segmentation mask allows you to really just create an image that has particular colors in it, which represent particular types of object. So if you want to create, for example, a room with a door in it and a bed in it, you can use particular colors to identify this is where I want to have a bed, and this is where I want to have something else.
By the way, you don't have to create these data types manually. So with the toolset and with diffusers come a bunch of additional methods of creating these inputs. So some of them, like for example, the segmentation over here, are done through neural nets. HEDs are, I think, also a combination of traditional image processing and neural nets. This is a traditional image processing. We also have a depth map extractor, which comes from automotive, which does monocular depth estimation. Yeah, and then, the other inputs that Paul mentioned.
Yeah, so with all of this stuff, now we've basically collected all sorts of reference data that we want to use to guide the generation of an image, which means that now it's time to solve it. And so what we can do, for example, is give this input image here. We can give it all the other prompts that we've given it, right? A text prompt, we can give it the guide image, we can give it the ControlNet things, and then at the end of the solver, we get an image. But not quite yet, because the solver still lives in latent space. So what the solver returns is, once again, latence, which we see represented here in the bottom of the image. After that, you plug it into an image decoder, which brings it back from the machine format, right, that machines understand, back to the image we see in the top right. Okay, so now that we've sort of seen the process, the nodes, and what we can do with it, let's talk a little bit about the development process of how we went about, developing this. So we worked with Google Colab, we've worked with various other things, which gave us a sample of code to work with that we just tried out, which we then analyzed. So that's the sample you see here on the left. After doing that, the process that I use is essentially looking at how can we get those individual nodes that we created on that Miro board from this code sample, right? So I've sort of moved all the parts that belong together to the same place in the code, which sort of already modularized it a little bit. After doing that, we just extracted all this code into individual modules on disk that would allow us to call these from wherever we wanted to call them from, which means that now you can do this entire Stable Diffusion process like you can see here on the right. You just import the node, right, that lives in Houdini that you want to use, and you can call it from anywhere. So this is just Python at this point, right? Since we have these modules on disk, seen here in the top left of the image, we can now just build our SOP network in Houdini, right? And then we have a Python SOP where we can just import our module, right, that we've modularized. We can import attributes that users have created that drive certain things. We can connect it to parameters that live on the node that allow you to modify things, and then just have it solve that, export out the attributes that you want, and you're good to go. So essentially what we're doing is we're converting from Houdini native data types, attributes, geometry, whatever it is, into a format that is used by these modules, right? Just in NumPy arrays or whatever it is, and then solve it, and then once again back to native attributes in Houdini so that users can do with it whatever they want.
Paul hinted at it. This was kind of how we work, and I love that you see here that mainly Paul is working and I'm just mainly eating and mainly am grumpy, which kind of represents how we work. Basically, I shot him a bunch of Google Colabs and tried to figure out what the code does, and he went ahead and implemented this. And I mean, well, this actually seems longer than it is. I think until we had a running prototype, it was literally the first afternoon or something like that.
Yeah, so after sort of modularizing that code, I said it'd probably take half a day in that video earlier. I checked on GitHub, it's actually 5 hours until it was all implemented in Houdini, the first version, of course,
The thing,
right?
however, is when you're working with Paul, you quickly notice this. Paul is one of those guys who can code while listening to what I then call techno.
It's not techno, it's
It
drum
is
and
not-
bass.
It's not techno. So yeah, that basically was my day in Monaco, and yeah, I apologize for the hair and for everything.
Yeah, but it works for me, so I like doing it. So that was in Monaco. So we had 9 days total there, of which 5 development days. While we were there, sort of this GIF here represents kind of the way we worked. We worked, fast, and we wanted to try lots of things, fail often, really learn what works, what doesn't, try something else, explore a lot. And then once we get home, we just slowed down, right? Different pace. We pivoted completely in terms of what do we focus on while working on this thing, right? Because now we have something we like, now we're going to refine it. So refining it, what does that mean? Well, for us, refining means find a small audience that you can give your tools to fast, right? So this is far from something you would release into production at this point. You want to just give it to people, get their first insights, see what they think, see what they want to do with it, and just get their raw feedback. Don't be worried about, yes, this is broken, this doesn't work. That's what you want to hear, because maybe you have to pivot a little bit into something else.
And the interesting fact that we got at the first feedback was, yeah, the installer needs a progress bar. Okay, super fine, that's a technical feedback. But once the thing was running, the first feedback we got from 2 or more users was, I have no clue what I should do with this. And we were like, okay, we're a bit dumbstruck by this, and we just went to sleep. And the next morning, we came on there, we had like a list of images and a list of stuff they came up with and generated. So it's quite astounding to see how quickly they took to it and how quickly they actually embraced it as a tool, although they were a bit flabbergasted at first.
Yeah, so after getting that feedback, lots of it has to do with, of course, quality of life, user experience. So that is, of course, also what we, looked at in terms of the tools that we've given people so far. So what you see on the left is the original interface for lots of nodes, and on the right you can see it's very, stripped down. It's not a lot there, except for the things that people really care about. Because when you work with Stable Diffusion, you have to control things like what's the width and height of the image, what's the latent width and height of the latents that you generate. But these are things that really are important to the system. They're not important to the user. And you have to identify those really quickly and abstract it out, because these are things that people shouldn't be setting. It's just stuff that they don't want to touch. You really want to give them control over things that allow them to modify the output and not so much the intermediate steps of getting them there. It's also a game of semantics. So there's a node called mask and code, which takes an input image and it takes a mask and it outputs something. Should the mask go on the left side or the right side? Difficult question, right? Or maybe it's not. But when you look at, for example, other nodes in Houdini, like copy to points, who here knows which goes on the left side? No one? The geometry or the points? I don't know. Yeah, it's difficult, right? So you really have to think about what is this node doing? What is intuitive? And adjust your nodes to, make it, be intuitive for users. It's also something you should be asking yourself. Perhaps I can color code these node in and output so that it's easier for people to know which, nodes wire together. And you might think, oh, that's a good idea, because then, you can just see what goes together. But does it make it easy for people to learn, or does it make it hard to use later on? Because at the end of the day, these nodes are not doing anything special. They're dealing with native attributes in Houdini and geometry. These colors have semantic meanings in Houdini, where, for example, pink is called constraints in Houdini. How does this fit in with the rest of Houdini? Does this just isolate it from the rest in Houdini, or does it make it easier or harder to learn? So perhaps it's better to just educate the people and have it learn once and make it easier to learn or use later on. Perhaps a better way is just using the other systems that Houdini has, which is giving the in and outputs a proper name, right? Because then perhaps it's a bit hard to get into at first, but afterwards they have the experience and they can use it and do some cool things with it. Then, of course, also take a look at the overall structure of the nodes. So initially, we sort of had our inputs and outputs wired all over the place, where we had the scheduler taking in the noise, as well as the guide image, but the mask went to the solver. Some parameters were on the scheduler, some parameters were on the solver. So it was sort of hard to really go to one node and tweak everything, which we cleaned up and made the scheduler node basically the node that just collects all the data, allows you to configure your solve, and then you plug it into the solve node, and it just does the solving. Why would you have to configure certain parameters in the solver, even though all it really just does is solve? So while working on tool sets like this, really have a think about what node does what, and how can I simplify this? Now we've seen some more stuff here. Let's show another example of what we can do. So here we have a photogrammetry scan with a result which has a piece that we don't quite like, or perhaps it's missing data. We can just isolate the area by masking it in Houdini with the group SOP, right? And then Stable Diffusion is just going to in-paint the area with something that makes sense. So what you see here is 3 results, right? The first one, the ugly one I call it, is the original source scan. The second one was a little bit blurry. That's just basically imagine as if the photogrammetry process just missed a part of data, right? Perhaps it didn't scan properly. And the third one is the fixed version of your photogrammetry scan. So as you can see, these tool sets is not just for 2D images. You can use it in 3D as well. Now that we've seen some practical stuff, let's go to some fun times. Yeah, working with lots of data in Houdini and printing it, it just freezes. So yeah, don't use print statements for large data. It'll just be oops, right? Now, another fun thing that we had is when we first got our first implementation of the Stable Diffusion process in Houdini, we got these images here, and I said, oh, cool, it all works, it's great. But Moritz said, what is this noise here? It doesn't make sense, all right? And I looked at the code, and it was, yeah.
And we had this hunch that it was some precision issue, again, like you mentioned. So yeah, and it took us a while, and we tried like, at the end we ended up setting everything to 64-bit floats because we were expecting like a minor comma going away when we realized we were reading in integers.
Yeah, so everything is latent, as you can see, right? Floats on the right side, but when you call point int attribute values, it just grabs all your attribute values.
Zeros and ones.
Yeah.
And I mean, it's amazing that it can produce that out of zeros and ones, but it's a bit noisy.
Yeah, so side effects, please, when you read floats as ints, give us a warning.
Yeah, this was also done by one of our beta users. He is really into PDG, and he used PDG to parse a comma-separated text file that contains song lyrics and uses it to automatically prompt and automatically render out prompt for lines of code. And he is really a Beatles fan, so he prompted, I think, yeah, for painting 70s animation, Yellow Submarine, Beatles, Heinz Edelmann, and Psychedelic. And these are some images that he generated, really automatically just going through the lyrics of Lucy in the Sky with Diamonds. Again, just connected with PDG to SOPs and even COPs to get this out. Yes. So one of those examples. And one of the last ones I want to mention that there's even more. I mentioned that this thing is all implemented on one certain library, that is diffusers. And the thing is now that Paul wrote a, I think, easy to use installer, I hope so, we have diffusers available in Houdini with a bunch of additional libraries for image metrics and for data extraction, data extrapolation. So what that means is that although you have these prefab nodes, what you can do is that with a few lines of code, you can get some other pipeline to work, some other algorithm to work. For example, in this case, one that is called instruct pix to pix, which takes an input, in this case an input sequence, most exciting sequence I've ever shot, and you prompt it with, turn this into a painting, turn this into a pencil drawing. The mustaches were not generated, no, your mustache might have been generated with that, and it outputs something like this. Again, could be tweaked, but this, for example, is temporally more coherent than your standard Stable Diffusion. And this is just a cheap example. So that is available now, and those pipelines can be set up within, I think, 6 lines or 7 lines of codes.
Yeah. And so with that, we're announcing machine learning operators, the bestest machine learning north of Niagara. And yeah, it's...
I don't know why you kept with it. That was literally meant as a joke I came up with, but it's now our official banner image. And you can get it at this address, which redirects you to the GitHub, where you also find this beautiful banner image, and where you can download the whole thing.
Yeah, so it's a free open source toolset that you can get right now if you want to play around with Stable Diffusion Houdini, do some cool stuff with it. and let us know what you think.
Yeah, please participate in the development. So if you find bugs, please do that. If you have feature requests, ideas, please do that. And with that, thanks so much for having us.